From this distant vantage point, the Earth may not seem very interesting, but for us, it is different. Consider again that dot. That's here. That's our home. That's us. Everyone you have ever loved, known, heard of, every human being who ever existed lived out their lives there. The sum of all our joys and sufferings of our species lived there on a mote of dust suspended in a sunbeam. These were the words Carl Sagan wrote when he saw this photograph taken by the Voyager 1 probe when it was 6 billion kilometers from Earth in 1990. At one moment, it aimed its camera at Earth and took this photograph. Seeing this image, one might feel very small, but that's normal because humans are indeed very small compared to the universe that surrounds us. The average human height is about 5 feet 7 inches, but this height has not made us afraid of heights. In fact, the tallest building we have built, the Burj Khalifa, stands an incredible 828 meters tall. It's so high that if you were at the base of the building watching the sunset, you could take the elevator to the top and watch the sunset again. However, its height is nothing compared to Mount Everest 8,848 meters, the tallest mountain on Earth, which continues to grow by about 4 millimeters per year. In California, Mount Whitney is of similar size, which is not very surprising, but what's more surprising is that its height is approximately the same as Pluto's radius. Now I understand better why it's not considered a planet. Speaking of planets, Earth, our planet, is astonishingly about the same size as Sirius B, the brightest known star. We often think the Sun is the brightest star, but it appears so bright simply because of its proximity. Another star similar in size to the Sun, Altair, has one of the highest known rotation speeds, spinning at an exorbitant speed of 250 kilometers per second, which causes it to have a flattened shape. If we move much further away, we reach VY Canis Majoris, which is, to date, the largest known star. Here you can see the size comparison with the Sun. To give you an idea, a plane would take 1,200 years to make a single orbit around it, as it measures to million kilometers in diameter. If we keep moving away, we no longer find stars, but nebulas, vast accumulations of interstellar dust that take on the most curious shapes, inspiring their names. Some are less than a light year across, like the Cat's Eye Nebula or the Hourglass Nebula, but if these seem large to you, know that they are actually among the smallest. The Ant Nebula measures an impressive to light years, meaning light takes 2 years to travel from one end to the other. Of a similar size are the Eskimo Nebula, the Rotten Egg Nebula, or the Boomerang Nebula, the latter being the coldest known object in the universe. Much larger are the beautiful pillars of creation, clouds of dust and gas measuring 10 light years in height. Sadly, they no longer exist, as a supernova destroyed them 6,000 years ago, but fortunately, they are 7,000 light years away, so we can continue to enjoy them for another 1,000 years. However, what truly breaks records are not these gigantic pillars, but the colossal Tarantula Nebula, the largest known, measuring 600 light years across. Let's go to an even larger level, that of galaxies. The Sombrero Galaxy is one of the smallest known, measuring a bit less than half of the Milky Way, but it is no less beautiful for that. Much larger is the galaxy NGC 4889, measuring the same distance as the Earth's orbit around the Sun since the solar system was formed. It also contains the largest known black hole at its center. If we move much further away, we find a Bell 2029, a group of galaxies that includes the largest known galaxy, 80 times larger than our own. It is too large to truly imagine. There are few things that exceed these sizes, and it is debated whether they should even be considered things. An example is the Eridanus supervoid, a vast region of the universe that is slightly cooler than the average temperature of the universe, contains nothing inside, and emits no radiation. This area remains a mystery to some astronomers, with some speculating it leads to a parallel universe. Continuing our journey, we come to the immense and colossal Sloan Great Wall, officially the largest known structure in the universe. It is a filament containing many galaxies, including ours, and measures 1.3 billion light years. It is too large to imagine, but to give you an idea of its size, it represents a part of the distance that separates the Earth from the Hubble Deep Field, one of the most ancient photographs ever taken. This photograph also qualifies as one of the most distant photographs ever taken, showing images of how the universe was 12 billion years ago, just 1 billion years after the universe was created. We are so far from it that the light has taken practically the entire history of the universe to reach us, and the galaxies we see probably no longer exist. But the photograph is a precious snapshot of how the universe has evolved throughout its existence. This limitation of the speed of light means that we can only see the part of the universe close enough for its light to reach us, so we are unaware of the actual magnitude of the universe in its entirety. In fact, we don't even know if it has a limit. We can only affirm that the observable universe is a tiny fraction of the universe, 93 billion light years. If you do some calculations, you'd expect a much smaller number, considering I mentioned earlier that light has had 13 billion years to travel. However, since space is expanding at an increasingly rapid pace, the first galaxies emitting that ancient light are now much farther away than they were before. Having reached these measurements, it's very difficult to grasp the size of the Earth compared to the entire universe. To give you an idea, it's the same as a virus compared to the entire solar system. Speaking of viruses compared to us humans are very small. What happens if we travel to the smallest scales? Humans are, although it may not seem like it, very large animals. It's true that there are many species larger than us, but if we do the math, more than 99% of them are smaller than us. If we start descending on our journey to the smallest, we find that the wavelength of microwaves, the distance between two wave crests, is approximately the same as a coin. Next time you heat something in your microwave, think of it as being filled with waves the size of a penny. Speaking of money, it's often said that it is filled with bacteria, but it surely doesn't contain specimens of Theomar gardneramibiensis, the largest known bacterium, which lives off the coast of Namibia and can measure up to a millimeter, enough to be seen with the naked eye. Descending a bit, we reach 100 micrometers, a tenth of a millimeter, which is the minimum size an object must be to be seen with the naked eye. Fortunately, we have microscopes that allow us to study things smaller than this, like Escherichia coli bacteria, the most studied organism in history. This well-known and famous bacterium can be beneficial or harmful and is found in everyone's intestines, colonizing newborns in just 2 days. Of a similar size to this bacterium are human sex chromosomes, or the wavelength of visible light. However, very different from bacteria are viruses, which are not considered living beings since they do not perform functions of interaction and nutrition. There is much controversy surrounding viruses. Some people consider them very simple living beings because they only perform one vital function, while others consider them highly evolved and complex because of their incredible ability to thrive. Essentially, viruses are entities that merely insert their genetic material into living beings to produce more genetic material that will travel encapsulated to another host. Bacteriophages, a type of virus, support this, as they resemble tiny extraterrestrial robots. Since we are talking about machines, let's get to transistors gates, which are smaller than what can be seen with an optical microscope, and amazingly, smaller sizes are achieved every day. Back to living things, the DNA in your cells is only 3 nanometers wide but extremely long. In a single cell, there are 3 meters of DNA. If you summed up the length of the DNA in your entire body, it would amount to 115 billion kilometers, more than 19 times the distance from here to Pluto, and that's just in one person. Fascinating. But let's go smaller, like cesium atoms, one of the elements with the largest atoms, similar to the wavelength of X-rays. This small wavelength of X-rays is what makes them so harmful to the body. Going even smaller, we reach picometers, the smallest distance visible with an electron microscope, also the size of a hydrogen atom, the most abundant element in the universe, making up 75% of all matter. In the gigantic pillars of creation, hydrogen is the primary component. We often imagine an atom's nucleus as something large, but the difference between the nucleus and the size of an atom is immense. To give you an idea, if an atom were the size of a football field, the nucleus would be only the size of a shirt button. Even more astounding is the vast empty space between the nucleus and its electron shell. It's so large that if you remove this distance in all the atoms that make up all the people in the world, all humanity would fit into a single sugar cube. This is why atomic nuclei are so small. Even the uranium nucleus, the largest natural chemical element, is similar in size to electrons, the particles in the atom shell. The size of electrons is still uncertain because quantum theory has shown that an electron's size changes depending on how you look at it. This phenomenon defies human logic, which is why quantum physics includes strange principles to explain particle behavior. One such principle is the uncertainty principle. Imagine trying to measure an electron's charge or size. You need to send a photon to detect the electron, but doing so changes the electron's properties. Therefore, simply observing an electron distorts the results because observation changes its initial properties. This is a bit how quantum physics works. For this reason, beyond the scale of magnitudes, known sizes are only estimates. Now that we've entered the small quantum world, we encounter peculiar particles called quarks that don't follow conventional physics laws. Their names don't seem logical, but are officially used by the scientific community. There are 6 types of quarks: up, down, strange, charm, top, and bottom. Quarks form subatomic particles like protons or neutrons. A proton, as we've seen, is incredibly small, made up of 3 quarks, making quarks even tinier. Interestingly, the smaller the quark, the more mass it has, with the top quark being 10,000 times smaller than the up quark, 100,000 times heavier. Fascinating yet nonsensical. Even stranger and more amazing are neutrinos, the smallest and lightest known particles, weighing 5 by 10, 36 kilograms. You might wonder what neutrinos have to do with you, but neutrinos are closer to you than you think. More accurately, neutrinos are within you. Every second, about 200 trillion neutrinos pass through you. Their small size allows them to pass through 200 Earths effortlessly, so neutrino detectors can be placed underground and are key to understanding our universe. At this point, it seems impossible to go smaller, but according to increasingly accurate quantum physics theories, it is possible to go much smaller, reaching quantum foam and strings. Quantum foam is believed to be the fundamental structure of the universe, and strings, thought to form all existing particles, create different particles based on their vibrations. Quantum strings are extremely small, slightly larger than the strings we see, like guitar strings or those used to tie things. The truly large strings are those composed of billions of galaxies forming a dense network throughout the universe. So, are we really large or small? In my personal opinion, what makes us large is our ability to recognize how small we are.